Hello everyone. Wave optics part 1, Huygens Principle. In this video, I will be discussing the Huygens Principle. Introduction. In introduction, I will be discussing the history of wave theory of light. At first, light was considered to consist of particles or the corpuscular model of light, which was given by Descartes in 1637, and he derived the Snell's law. Isaac Newton further developed the corpuscular model of light in his book Optics. It was in 1678 that the Dutch physicist Christian Huygens put forward the wave theory of light. And Thomas Young performed his famous interference experiment in 1801, which established that light is indeed a wave phenomenon. The wavelength of visible light was measured and found to be extremely small. For example, the wavelength of yellow light is about 0.5 micrometer. Because of the smallness of wavelength of visible light in comparison to the dimensions of typical mirrors and lenses, light can be assumed to approximately travel in straight lines. Then, in the 19th century, Maxwell was able to prove that light was a form of electromagnetic wave and hence it doesn't require any medium for its propagation. That is, Maxwell could calculate the speed of electromagnetic waves in free space, and he found that the theoretical value was very close to the measured value of speed of light. From this, he propounded that light must be an electromagnetic wave. Thus, according to Maxwell, light waves are associated with changing electric and magnetic fields. And this changing electric field produces a time and space varying magnetic field, and a changing magnetic field in turn produces a time and space varying electric field. The changing electric and magnetic field result in the propagation of electromagnetic waves or light waves even in vacuum. Now we can see the Huygens principle. Huygens principle states that each point of a wavefront is the source of secondary wavelets, which are small waves which spread in all directions with the speed of the wave, and a locus of points which oscillate in phase is called a wavefront. The speed with which the wavefront moves outward from the source is called the speed of the wave, and the energy of the wave travels in a direction perpendicular to the wavefront. If we have a point source emitting waves uniformly in all directions, then the locus of points which have the same amplitude and vibrate in the same phase are spheres, and we have what is known as a spherical wave. A large distance from the source, a small portion of the sphere can be considered as a plane, and this is called a plane wave. These are as shown in the figure. Now, if we know the shape of the wavefront at t is equal to 0, then by the use of Huygens principle, we can obtain the shape of the wavefront at a later time tau. Thus, Huygens principle is essentially a geometrical construction which, given the shape of the wavefront at any time, allows us to determine the shape of the wavefront at a later time. According to Huygens principle, each point of the wavefront is the source of secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. These wavelets emanating from the wavefront are referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at a later time. In this figure, we can see an initial wavefront f1, f2. Now, after a time interval tau, we have to find the position of the new wavefront. Here it can be seen that the new position is found out by drawing a tangent to spheres with radius V tau. Thus, if we wish to determine the shape of the wavefront at t is equal to tau, we draw spheres of radius V tau from each point on the spherical wavefront, where V represents the speed of the waves in the medium. If we now draw a common tangent to all these spheres, we obtain the new position of the wavefront at t is equal to tau. Now we can use Huygens principle to explain refraction of a plane wave. For that, we can consider an interface PP' which separates two mediums having light velocities v1 and v2. AB is an incident wavefront in the direction A'. Now, after a time interval tau, the wavefront reaches the point C, such that BC is equal to v1 tau. Now, in order to find the refracted wavefront, we will draw a sphere with radius v2 tau from point A. And if we draw a tangent to this sphere EC, which is the refracted wavefront, and AE is equal to v2 tau. Here I is the angle of incidence and R is the angle of refraction. Now from triangle ABC, sin I is equal to BC by AC, that is equal to V1 tau by AC. And in triangle AEC, sin R is equal to AE by AC, that is equal to V2 tau by AC. Therefore, sin I by sin R is equal to V1 by V2. That is the ratio of speeds of light in the two media. Now, if we take the refractive index of medium 1, N1, which is equal to the ratio of the speed of light in free space to the speed of light in medium 1, which is C by V1, and N2 is equal to C by V2. We get N1 sin I is equal to N2 sin R. This is the Snell's law of refraction. Now we can prove that the frequency of the light wave remains the same even after refraction. That is, let the wavelength be medium 1 be BZ and the wavelength in medium 2 be equal to AE, that is lambda 2. Therefore, lambda 1 by lambda 2 is equal to BC by AE, which is equal to V1 by V2. Or V1 by lambda 1 is equal to V2 by lambda 2. Thus, we can see that the frequency remains constant while the speed and wavelength decreases. Now, refraction at a rarer medium. The figure can be obtained similar to the previous case. In this case, I is lesser than R. That is, the refracted ray bends away from the normal. It shows that the speed of light in medium 2 is higher when compared to medium 1. Now, N1 sin I is equal to N2 sin I. In the case of refraction at a rarer medium, there is a special phenomenon which can occur known as the total internal reflection. This occurs when the angle of incidence is greater than the critical angle. Critical angle is the angle at which the refracted angle equals 90 degrees. That is, if I greater than IC, there will be no refraction and total internal reflection of wave takes place. Now we can explain reflection of plane wave by plane surface. For that, we can consider a plane surface M. Let the incident wavefront be AB. Now, after a time interval tau it travels to C. Now we have to find the position from A. For that, we can draw a sphere with radius v tau, where v is the speed of light in this medium and tau is the time interval. Now if we draw a tangent to this sphere, we get the reflected wavefront, which is easy. Here I is the angle of incidence and r is the angle of reflection. So BC is equal to V tau and A is equal to BC is equal to V tau. Now comparing the triangles EAC and BAC, we find that triangle EAC is congruent to triangle BAC. Hence the angles I is equal to R, or the angle of incidence is equal to angle of reflection, which is the law of reflection. Now we can see the application of wave theory to some phenomena. This is the case when light passes through a prism. When light passes through a prism, the incident plane wave gets bent as shown. This occurs because the speed of light in glass is much lesser than that in air, and since the wave have to travel much greater distance through the base of the prism, it gets bent as shown. In the case of a thin lens, the incident plane wave gets converted to a spherical wavefront of radius f, which is converging. Similarly, in the case of a concave mirror, an incident plane wavefront after reflection from the concave mirror gets converted to a spherical wavefront of radius r by 2, where r is the radius of curvature of the concave mirror. The case of a concave lens and a convex mirror can also be explained similarly. Now we can see the Doppler effect of light. Doppler effect is the shift in frequency of light when there is a relative motion between source and observer. Astronomers call increase in wavelength due to Doppler effect as redshift, since the wavelength in the middle of the visible region of the spectrum moves toward the red end of the spectrum. When waves are received from a source moving toward the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. The Doppler effect for light is very important in astronomy. It is the basis for the measurements of radial velocities of distant galaxies. So this is the end of this video. In this video, I have discussed mainly about the Huygens principle. If you have got any doubt, please comment in the section below. Thank you.